So hello everyone, my name is Amrish Singh, and I wanted to show you how you can use this TST software to generate toolpaths that is of a continuous nature with closed loop properties with the same start and end points. To use this software, as you can see, it's open on my screen here. You simply have to open the folder that was shared with you, and you have to launch this tst.exe. Just simply double click on it and wait for a few minutes, and then it will launch into this GUI. The first thing that you need to do is you need to import a boundary. So if you want to create your own boundary, I have a video for that as well, and I'll provide you a link to that video. But the test boundary, this is a test boundary of a rabbit, the contour of a rabbit, and the format of it is just simply XY coordinates. So the first column is the X coordinate and the second column is the Y coordinate. And you will notice that the first coordinate, that is 14.3 and 9.4, would be the same as the last coordinate, 14.3 and 9.4. So it's a closed loop contour plot. So I will just copy this link directory and then go to import boundaries and simply paste here, and then here it is, rabbit. Click on it and then click on open. Launch it in full mode. So this is the contour that has now been imported. Uh, then you need to specify a step over value. That means what is the distance between two beads that will be deposited. Let's say it's an FTM printer. So what is the distance between the two beads? So let's say we'll keep it as the lower the step over you have, the finer the digitized grid would be, and it will take a lot more time to digitize. So we have step over 2, and what type of a digitization do you want? If you want a rectangular or a circular one, we'll look into these later. But if you want a rectangular, simply click on it and then click on digitize. And then so you have these points are created inside, and down you can create calculate toolpath, and you see here that you will get the toolpath from here. You can also have okay, so one thing that you can notice here is that the toolpath extends beyond the contour just over here, which will mean that my step over is too high. So I can just let me reduce it to 1, digitize again. And now if I click on calculate toolpath, so once you calculate toolpath, you need to wait a little while so that it calculates. Yes, so now you can see that this is a much better results. The toolpath is inside the contour. There is another method of digitization which actually trims the toolpath which was extended beyond the contour. So to do that, I will just switch this back to 2, and instead of method 1, I will click on method 2 and click on digitize. Now you can see that some of the digitized grid points are outside the contour. And now if I click on calculate toolpath, you will see that most of the toolpath has extended beyond the contour, and also the contour is missing. What you can do here is you can just click on this trim toolpath. So now you can see that everything is back inside the contour. The toolpath which was extended beyond the contour has now been trimmed with the contour that you provided. If you want to know more about this, there is a paper that was published. Originally, this work was done by Sadaival, and so I can link to the works that we published based on these TST software and the toolpath. Okay, so that's the rectangular one. We can also, let me switch back to method 1, and I want to show you the circular. So if I click on circular and then digitize, you can see that the center of this is located in the mid geometry. If you want to have it at the centroid of the shape, you can just simply click on it and click on centroid, and then click digitize. You can see that now the center of the digitized grid is at the centroid of the shape. You can also give your own manual X and Y points for the center, grid center. So let me just keep it at centroid and lower the step over values, and then click on digitize. You can see that the grid is digitized. If I click on calculate toolpath, it's going to launch the LKH solver. Yeah, and then you have the toolpath. So one of the properties that we have is we can bias the toolpath to favor one direction over the other. So let's say I bias it in the cell width direction. So I'll just enter in 0.95 and click on digitize. And if I click on toolpath, calculate toolpath, the toolpath that you're going to get, again, we need to wait for a while. You can see that it is favoring the azimuthal direction. That means it's more circular than it is radial. If I do the other way around, so I will make it 1 and 0.95, click on digitize, and then again click on toolpath, calculate toolpath. So you need to click on it and wait a little while. Now you can see it's much more radial. Maybe more I should do. Uh, Click on digitize. Yeah, so now you can see that it is much more radial than it is circular. So depending upon, so this is just a bias that you can introduce, which will force the toolpath to favor one direction over the other direction. So these are just the bias options. If I go back to rectangular, I can switch between horizontal favoring and vertical favoring. So let's say I want to bias it in the width direction. So I will enter in a value which is less than 1. Click on digitize. So this essentially means it's a factor of step over. So the grid points in one direction is 0.95 times step over, whereas the grid length is equal to step over. So that is how the bias is actually calculated. So again, if I click on calculate toolpath, um, see, you can see that the toolpath is much more horizontal favoring than it is vertical favoring. Also, let me show you the other way around. So you can just simply do this, click on digitize. Now if I click on calculate toolpath, you will see that the toolpath is much more vertical favoring than it is horizontal favoring. You can see. Another thing that you can do is you can click on view parameters, and this view parameters will tell you how many turns are there, what is the length of the toolpath, and what is the efficiency of area filling. Again, this is something that we talk extensively in our paper, and I'll link to both the papers in the video. So if there is no bias, you can see that the number of turns would be significantly higher. If I click on digitize and click on calculate toolpath, uh, and then if I click on view parameters, you can see that the number of turns is significantly higher. Okay, so that is how you can generate toolpath which gives you uniform density. You can also use this software to create gradient in the density by specifying either a gradient function or by a density map. So let's see how we can do that. Again, I'm going to go to import boundary, and I will go to this directory here, and I'm going to import this time a very simple geometry. It's a simple contour. It's a simple 50 by 50 contour, and I need to create a gradient density toolpath inside this contour. This time, when you select on digitization options, so the grid options, you'll select either force mesh rectangular or force mesh circular or force mesh adaptive. So let's say I'm going to select force mesh rectangular. The step over, let's keep it as, okay, let's reduce it to 1.5 maybe. In the density function, I already have a density function here. So I'll just copy this and paste it here. So what you must do is the syntax in which you need to specify the density function is the same syntax of writing a Python script when using either NumPy library or math library. So if you were to use these two libraries inside Python and plot, let's say, some function, the syntax you would follow there is the same syntax you need to follow here. So I've specified this. Um, Again, this is using a function. There are other options as well. You can use an image, which I'll show you, or you can use this is for a different application. We'll go back here, and then we can simply click on digitize. and you can see it progresses. There are number of iterations. So each of these iterations is trying to conform the grid, the density grid, to the function that you specified. The longer iterations, if they increase the number of iterations, the more strongly it will conform to the function, the density function that you have specified. So now you can look at the digitized output, and what you are seeing here is this function, the grid, the density is following this function, is this gradient, meaning that if you were to put at this x location, you were to put 0 on the extreme left, so the density is going to be 100%. And if you were to put in place of this x, if you were to put 50, so the density is going to be 0.5 or 50%. So 100% on the extreme left hand side to 100%. I'm sorry, 100% on the extreme left hand side to 50% on the extreme right hand side, and there is a linear gradient in the density. So this is how you can specify density function. I have some other example of density functions as well, and you can try this out. I will share all these density functions. There are some other density functions as well which I used in our paper, and I'll share those density functions as well just for you to play around. So once you have digitized this grid, you can click on this calculate toolpath, and again it's going to call the solver, and we need to wait a while. Yeah, so you can now see that there is a gradient in the toolpath. The toolpath has been calculated. We can also create this density using a rectangular grid. So again, I will keep it to centroid. The density function is same as we specified before. And now if I click on digitize, and it's going to progress. To wait a while, and then we can see you click on digitized output, and you can see again the grid remains circular, but there is a density in the gradient where you have higher density on the left and lower density on the right. 100% on the left and 50% on the right. You can again bias these grids. So the way they work for uniform density, they would work for gradient density as well. So if I were to just, let's say, click on calculate toolpath, it will calculate the toolpath. And now if I were to just bias it, so again I have specified a bias value. I will click on digitize. So this should give you digitization in more azimuthal direction, bias of the toolpath in the azimuthal direction. So we can click on digitized output, and if I click on calculate toolpath, these are not, it's not very clear. Let me bias in the other direction. So bias it here, click on digitize. Click on digitized output, and then we'll click on calculate toolpath. Yeah, so this is more circular, and the earlier that I did was more radial. It was moving outwards from center, more radial, and this is more circular. So let me lower it down and see what happens. More bias. So if I click on digitize, I think it would be much more clear if I lower this bias value. And then click on digitized outputs, and then calculate toolpath. Yeah, so it's much more circular than it is radial. So if I were to just simply switch this, so it will be much more radial than it is circular. And then click on digitize. Click on digitized output, and if I click on calculate toolpath, you can now see, yeah, it's much more radial than it is circular. So while having the density gradient, while preserving the density gradient, you can bias the toolpath in one direction or the other. Okay, so you can also have an force mesh uh, adaptive toolpath, which is where it tries to follow the toolpath, tries to mimic the contour itself. So to demonstrate this, I think it will be better if I imported the rabbit contour again, because it has a complex contour, so it will be much more clear from there. Okay, so now again I have imported the rabbit contour. Let me first show you without any bias. The density function remains the same, and now I will just simply click on digitize. So if there is, if you notice that the software is hanged or something, then you need to close it and restart it again. Or sometimes you can also just click on digitization again, and it will start digitizing. So you need to fiddle around a little bit to get it okay to work. So now you can see here that there is again the gradient is followed. It's not very clear. Let me reduce the step over. Click on digitize. Click on digitized output, and now if I click on calculate toolpath, you will see that the toolpath is adaptive. That means it is trying to mimic the contour itself. So let me do this, and then it will be very clear. Let me bias it, let's say in the width direction. So in this adaptive grid, what you have is the contour, and there are two directions. The one direction is where the toolpath is perpendicular to the contour, and the other direction is where the toolpath is parallel to the contour. If you are familiar with contour parallel toolpaths, so there could be two directions. Either you are perpendicular to the contour, or you are following the contour parallel to the contour. So there could be these two directions, and you are biasing the toolpath in these two directions. Let's see, if I were to give 0.75 in the first column, in this first cell here, and if I click on digitize, let's see what results do I get here. Just click on digitize again. Yeah, it's just finished. Click on digitized output, and if I click on calculate toolpath, we'll wait a little while. Yeah, so now what you're seeing here is the toolpath is trying to be orthogonal to the contour. It's trying to be perpendicular to the contour. But if I were to just simply switch this, the toolpath will try to be parallel to the contour. So I have just simply swapped these two values. I can click on digitize. Here, click on digitized output, and then click on calculate toolpath. And now you're seeing that the toolpath is trying to follow the contour. Okay, it's trying to be parallel to the contour than it is orthogonal to it. And all of this is done while preserving the gradient in the density. So higher gradients on the left, higher density on the left, and lower density on the right. So this is how you can use the density function. If you go to stopping criteria, from here you can change how many iterations you want it to progress to. So currently it's set to 150. You can increase it, and this is where you can specify that when do you want the number of iterations to stop. Either you specify how many iterations, or you specify when you want to stop the iteration. That means if the movement of these grid points, when it is trying to conform to the density function, is below a certain value, then it will stop automatically. Okay, so far we have looked at how to generate uniform density toolpath and a gradient density toolpath, but the generation of the density gradient was done by specifying a density function. You can also use a grayscale image to specify. Let's say I have already provided to you this density map. So it's just a grayscale image, and this grayscale image, what it does is it specifies to the software that what are the locations that will be of higher densities. So the locations which are white, the regions which are white will be of higher density, and the regions which are dark would be of lower density. And it needs to also extract the contour from this image. So wherever there is a threshold set, so you see this uh, this slightly grayed out rectangle has a background which is black. So we need to extract the contour between these two rectangles. So how we can do that? Let me copy this folder location. We'll go back to our software. Um, we will click on whichever grid we want to generate the gradient density for. So let's say I want it for this force mesh rectangular. We can come to density function, and instead of specifying a function, use a function. I'll just click to image. So I now want to use image. Having clicked on this image, I will go to import density image map. We'll navigate to the folder where it was saved. The density map was saved. The grayscale image was saved. So it's this one, picture one. Click on open. Now you can see that the image has been imported inside our software. And now what we need to do is we need to get boundary from the image. We can also specify that how many pixels correspond to what length in reality. So we can also scale up or scale down this density image, this density map. So now we click on get boundary from image, and you see as soon as we click on it, we see a green boundary, a contour appear. Now we can go back to our previous options here, and let me reduce the step over to 1, and I can click on digitize. So if you see that it's not moving forward, just try to click on it again, and it should progress. Yeah, now it progresses. Sometimes you need to click on it a few times and it progresses. And now if you see the status here says 10, if you click on digitized output, you can see that the points are clustered. So there is a higher density of digitized grid points on the region which was white. So you see this was the region which was white, and you can see correspondingly this is the region which has higher density points, and this is the region which has lower density points. And now you can click on calculate toolpath. Give it some time, and you can see that the toolpath is now created. You have lower density here, higher density here. And with this image, all the usual options of biasing the toolpath and selection of any of these gradient-based digitization methods is applicable. Another thing that you can do here is you need to, if you want to extract the toolpath or the XY coordinates, you can simply go to File, Export, and you can click on this TST output. So if you click on it, just give it a name, test for TST coordinates, coordinates, and click on save. So a text file will be created here with your coordinates. Yeah, here it is. So these are the coordinates. And if you were to plot this, you will get the same toolpath which was being shown here. Okay. You can also use this software to create your toolpath by importing in a pre-digitized points. So let's say I have a bunch of points that were pre-digitized. By pre-digitized, I meaning you used some other software to create those grid points, and now you want to run the LKH solver to generate a continuous toolpath. So here, if you look at this text file, points text file, you see it already has the grid points, and I used a different software to digitize them. I just simply want to use the TST solver to connect these grid points in a manner which is continuous and has the common start and the stop point. So you can do that as well. So for that, what you need to do is just click on import digitized points, go to this folder where you have your XY coordinates for the digitized grid, click on open. So now you see that there are number of points that I have digitized from some other software. Now I want to just connect them using an LKH solver. So I imported those grid points, and now you can click on calculate toolpath. We'll give it a few seconds because there are a lot of grid points here, and you can see that this is the solver which is being launched. And now you can see that the toolpath has now been created. So this is how, if you have, and of course you can export this now. So you can export and you can click on TST output. So the order in which these points are to be connected will now be resequenced. So I will let TST imported grid points, click on save, and now you can see here um, that again the sequence has now been altered. And now if you were to just plot this in some other plotting software, let's say Excel, you will see the toolpath. Uh, More on both the how the software actually functions and um, the behind the scenes and how the algorithm actually works have been published in two works. So this work was originally done by Sadaival, and more about his work you can read through it in these two papers. The first one is in additive manufacturing, which is utilization of a TSP solver for generating non-retractable direction favoring toolpath for additive manufacturing. And the second one is in the Journal of CAD, and this is where you can read about how you can create density gradients. So one of the case studies that we did was creating a density function that is of Gaussian nature, and the peak of the Gaussian is at the centroid of the shape. So if let me see if I can show you a high resolution image. Yeah. So you see that this is the function, density function, and the peak of the function is at the centroid of the shape, and you see the x minus 25 and y minus 21. So these 25 comma 21 is the location of the centroid of this shape, and we created this density function, and you can see we can create these toolpaths. Okay, so that's it from my side. If you have any questions or queries, you can always email me, or you can give me a call anytime. All right then. So yeah, thank you very much for your time and attention.